So we finally made it to chemical bonding. Good old bonding. Now we could do some funny bonding jokes. What kind of bond are you, James? James Bond. Or yo mama's so rude, not even flooring would bond with her. Oh. Okay, moving on. There are two types of bonding that we're going to talk about. There's ionic bonding. It involves a transfer of electrons. So one element loses electrons and the other element gains electrons. It is a metal to a nonmetal within the bond. Covalent bonding involves a sharing of electrons. Atoms will share in order to reach a stable electron configuration. That is nonmetal bonded to a nonmetal. The octet rule. Atoms will gain or lose enough electrons to make them isoelectronic with a noble gas. There's that word, isoelectronic. It means, if you don't remember, it means you have the same number of electrons as another element on the periodic table. So in this case, you look like a noble gas. Remember, every element on the periodic table wants to look like a noble gas because they're stable and they're happy, they're noble, they're rich, and they can slap people when they want. That may not be true, but the rich seem to get away with that. Now, the exception, which we all should know, is hydrogen and helium because they only have one energy level and their outer shell, when it's completely filled, is only 2 electrons. All the other ones, all the other atoms, will they will have 8 electrons in their valence shell, their outermost energy level. Electron dot structures, or Lewis structures. We should be very familiar with these. It's a way to show the number of valence electrons in an atom. It really helps when we start to get further along in this unit, showing the actual bonds, drawing them on paper. But let's recap this. Valence electrons must be labeled like the following. You put the atomic symbol down, and then you're going to add an electron, but not in this order. We did not teach you this way, so you do not have to write this. What you do have to write is an electron will go at 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Then it would go back to make a pair of electrons at 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock for a total of 8 electrons, representing a filled outer energy level. So let's talk about the periodic table because we love it and it's awesome and it's pretty and we dream about it. The number of valence electrons can be determined by the group the elements are in. Only in the S&P block, though, because those stinking transition metals are special, and they're not going to let things be easy. We'll keep it at that. Group 1 has 1 valence electron. We should know this. Group 2 has 2. Now, if you skip to group 13, or 3A, we've called it before, that has 3 valence electrons. 4A has 14. 15 is 5, 16 is 6, 17 is 7, and 18 is 8 valence electrons. Here's some examples of an electron dot or Lewis structure. For group 1, lithium has 1 valence electron. Beryllium has 2. Boron has 3. Carbon has 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7, and neon has a filled outer shell of 8. Now, if you don't understand how to do this, you need to let Mrs. Flint or myself know, because we need to know how to do Lewis structures and where we're getting that information from. So, the valence electrons determine the chemical reactivity. So that means something we've already know or covered last chapter. Elements in the same group behave the same way. And it makes sense because the outer electrons in the outer energy level, the valence electrons, are the ones actually interacting with the rest of the world. You just can't bypass them to the lower energy levels. It just doesn't work. It requires too much energy, and it just doesn't happen. Doesn't work. So that's why we say the valence electrons are what make reactions happen. If you're in group 1, you're going to lose 1 electron to look like a noble gas. Why do we want to look like a noble gas? Well, because we've been telling you for a week or two now that every element on the periodic table wants to look like a noble gas because they are rich and they're snobby and they get a cool hat and can slap people when they want, or at least they get away with it. Anyway, group 1 loses 1 electron to look like a noble gas. Group 2 loses 2. Group 3 would lose 3 instead of gain 5, to look like a noble gas. Now, here's the one that can go either way. And some of you all had carbon and silicon for your mystery element. And I was like, well, it could go both ways. And it's true. They can either lose or gain 4 electrons. And it just depends what kind of bond they're making or atom they're bonding to that will determine that. Now, we're in the gain section. Group 15 will gain 3 electrons. 16 gains 2, 17 gains 1. And smiley face. Noble gases in group 18 don't want to lose or gain anything, so they get a smiley face. Now, what does that charge look like? Now, remember, if you remove, or gain electrons, you're affecting charge. If I take 1 negative electron away, I'm left with more positive protons, so that means I have a +1 charge. If I take 2 electrons away, I will have an overall +2 charge because I have more protons than I do electrons. Same thing for losing 3. Group 14 can swing both ways, positive or negative 4 charge. Now a negative charge. Group 15 has a -3 charge because if I add 3 electrons, I have more negative charge than I do protons, which means I have an overall -3 charge. I'll have a -2 charge for group 16 because I gained 2 electrons. I'll have a -1 charge in group 17 because I gained 1 electron. And of course, smiley face. So let's review electron configurations for ions. Remember, an ion is simply a charged particle, a charged atom. And we do that by adding or removing electrons. So let's do magnesium 2+, which happens to be in group 2. So we should know that it's going to have a +2 charge. But when we do the electron configuration for it, it would be 1s2, 2s2, 2p6, and that's neon. Well, it's not neon. You're still magnesium. You just took 2 electrons away, and now you look like neon because your outermost shell is filled. Phosphorus, if you gain 3 electrons, your electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, and that's argon. So 18 electrons if you add all those up. And you're more stable because your outer shell is completely filled. So let's do a small little introduction on ionic bonding. Before we do that, let me mention here, if you don't know how to do electron configurations, if you're not comfortable with it, you need to tell Mrs. Flanner or myself so we can make sure that we can get you to a level of understanding that will be very useful for the rest of your chemistry careers. Okay, it's the introduction to the ionic bonding. An ionic bond forms from the attraction between positive and negative ions. We've already said this. An ionic compound is made up of crystals. Ooh, shiny. Hey, they're not all shiny. Anyway, a crystal consists of a 3D repeating pattern of alternating positive and negative ions. That's cool. Let's talk about a formula of the unit. The lowest whole number ratio of ions. It is the empirical, which means the simplest formula for any ionic or covalent bond. So we know the lowest number, whole number that is, because you can't have points of an element, point of a bond. It's the lowest whole number ratio of ions represented in an ionic bond. And we'll get to that later on where we actually are drawing Lewis structures. Ionic compounds have high melting points. Fun fact, they conduct electricity when melted or dissolved. Fun fact, an example of that, a famous example would be table salt. NaCl, sodium chloride. Put that in water, mix it up. Yes, it can conduct electricity. So who's brave enough to put a tub full of distilled water and stand in it and drop a toaster? Don't do it. Don't do it. Theoretically, it would not. Distilled water, I mean, there's nothing in it except H2O. It would not conduct electricity, but there's so many things in that tub that there might be enough ions where it could, and then you would electrocute yourself. And there's a shape of a crystal. And I'm blabbing about cool things and not about the notes. Isn't that interesting? We are done with the notes. Go ahead and start the worksheet.